Did you know that jet engines, the powerful units that propel airplanes, can spin over 10,000 revolutions per minute and handle temperatures exceeding 2,500 degrees Fahrenheit, which is hotter than lava? Engineers work tirelessly to ensure that these technological wonders would survive the harshest environments on and above Earth. Today, we're going to uncover the fascinating steps involved in making a jet engine. From their ultra-strong materials designed to withstand extreme heat to the detail-oriented process that shapes each part. To better understand how jet engines are made, we first need to understand the basics of how they work. It all begins when air is sucked into the front of the engine. This air is then squeezed into a much smaller space by fans, making it tight and compact. Next up, we mix this compressed air with fuel, which is usually a type of kerosene. When we light this mixture, it explodes with a lot of force. This explosion shoots hot gases out of the back of the engine super fast, and because of this, the plane gets pushed forward. This push is all thanks to a famous rule called Newton's third law of motion, which tells us that for every action, there's a reaction in the opposite direction. Inside the engine, there are turbines that capture some of the energy from these hot gases to keep the engine running smoothly. This cycle of sucking in air, compressing it, exploding fuel, and shooting out gas keeps the engine roaring and the plane moving through the sky. Now that we know how a jet engine operates, let's look into how one is designed and developed. The process starts with a team of engineers brainstorming and sketching out ideas, focusing on creating an engine that's both powerful and efficient. They consider everything, from the size and shape of the engine to how it will handle different flying conditions. Once they have a solid plan, it's time to bring those ideas to life, virtually at least. Using advanced computer simulations, engineers test their designs without ever building a physical model. These simulations are incredibly detailed, allowing the team to see how different parts of the engine will react under various conditions. They can adjust airflow, temperature, and even simulate the stress that parts will face during a flight. This stage is important because it helps catch any potential issues early on, saving time and money and ensuring the final product is as safe and reliable as possible. Moving on to what goes into making a jet engine, let's talk about the materials used. Choosing the right materials is very important because they need to withstand extreme conditions like high temperatures and intense pressure. Most engines are made from a mix of superalloys, primarily titanium and nickel-based alloys. Why these materials? Well, titanium is incredibly strong yet light, which helps keep the overall weight of the aircraft down. Nickel alloys are great at resisting corrosion and can handle very high temperatures without melting. Engineers also use ceramic and composite materials in parts of the engine that face the highest temperatures. Ceramics can endure heat even better than metals and don't expand much, which keeps the engine stable and efficient. Each material is chosen based on its ability to meet specific needs within the engine, balancing durability, weight, and resistance to heat and wear. This careful selection helps ensure that the engine will perform reliably under the tough conditions of flight. With the right materials chosen, it's time to get into how the components of an engine are made. This process involves a variety of manufacturing techniques, each suited to creating different parts of the engine with precision and durability. The process starts with casting and forging, especially for the larger components like the engine casing and turbine discs. Casting involves pouring molten metal into molds, where it solidifies into the desired shape. Forging, on the other hand, involves shaping metal using localized compressive forces, which enhances the strength of the material by aligning and stretching the grain structure. Both processes are important because they provide the structural integrity needed for the engine to withstand the stresses of flight. Next up is machining, which refines these cast or forged parts into their final forms. Precision machining uses computer numerical control, CNC machines, that carve, drill, and mill the components to high tolerances. This step is essential for ensuring that all parts fit together perfectly and operate smoothly. The precision of CNC machining allows for complex shapes and features that are crucial for the efficient performance of jet engines. Next is additive manufacturing. Known as 3D printing, additive manufacturing is increasingly important in jet engine production. This technique builds parts layer by layer from metal powders, using laser or electron beam melting. It's particularly useful for creating complex, lightweight structures that would be difficult or impossible to make with traditional methods. Creating complex cooling channels inside turbine blades is an example of this. Next is surface treatment and coating. Once these parts are shaped, they undergo various surface treatments and coatings to improve their properties. Techniques like heat treatment are used to increase strength and durability, while coatings are applied to protect against corrosion and thermal damage. The culmination of these processes results in components that are ready to be assembled into the final jet engine. Each step is critical, from casting and forging that set the foundational strength through machining that ensures precise dimensions to additive manufacturing that allows for customization of complex parts. This detailed approach to manufacturing not only maximizes the engine's performance, but also enhances its safety and longevity in the demanding environment of flight. The next and most important stage after the manufacturing of every jet engine component is assembly. In a specialized facility, skilled technicians and engineers carefully put together hundreds of parts. The assembly process starts with the larger structures, such as the fan and compressor sections, followed by the addition of smaller, complex parts like fuel injectors and blades. Each component is carefully inspected and positioned, often with the aid of precision tools and computer-guided systems to ensure perfect alignment. The process is highly methodical, with each step following strict protocols to guarantee the engine's integrity and functionality. Bolts, screws, and rivets are all tightened to exact specifications, ensuring that nothing is out of place. This phase is crucial because the proper assembly of the engine ensures its optimal performance and safety in the air. Once assembled, each jet engine must undergo a series of rigorous tests to ensure it meets all safety and performance standards. This phase is critical in verifying that the engine can operate under various conditions without failure. Initial tests, often conducted on test stands, simulate the engine's performance in different flight scenarios. Engineers monitor everything from fuel efficiency and power output to vibration and noise levels. One of the key tests is the endurance test, where the engine is run at full power for extended periods to simulate long flights. This helps identify any potential wear and tear issues that might not be apparent in shorter runs. Another essential test is the temperature resistance test, which ensures that the engine can withstand extreme heat without degradation of its components. Vibration testing is also very important, as it checks the engine's structural integrity under stress. Any unusual vibrations can be a sign of issues with the assembly or individual parts. Afterward, the engine must pass a final inspection, which includes a detailed check of all its systems and components to ensure everything is working correctly and safely. After passing all necessary tests, the jet engine is ready for installation onto the aircraft. At this important stage, a group of highly trained engineers carefully attaches the engine to either the wing or the fuselage, depending on the type of plane. Connections for fuel, electricity, and hydraulics are secured, ensuring that the engine communicates seamlessly with the aircraft's systems. Once installed, the engine undergoes a series of ground tests to check its integration with the aircraft systems. These tests include running the engine from idle to full power while stationary and verifying all operational parameters are met without any issues. Technicians check every system for leaks, vibrations, or alignment issues. Only after these final checks will the aircraft be cleared for flight testing. The ultimate test of a jet engine's performance and reliability comes during the flight test. This key step involves taking the aircraft into the air, where pilots and engineers perform a series of maneuvers and procedures to push the engine to its limits. They monitor how the engine behaves in various flight conditions, including takeoff, climbing, cruising, and landing. Data on fuel consumption, response to control inputs, and efficiency at different altitudes are collected. Safety features and emergency response protocols are also rigorously tested to ensure the engine performs reliably under potential failure scenarios. This real-world testing is vital for assessing the engine's performance and gathering final data to confirm its readiness for commercial use. After investigating the delicate steps from material selection to rigorous testing, we have seen how important and complex jet engines are in modern aviation. As technology advances, these engines continue to evolve. What innovations do you expect to see in the future? Leave your thoughts in the comments section below.